Hello everyone! Today we will be learning about circular and periodic functions. So this is 12.6 in our textbook. So we'll cover circular functions. Those will have a lot to do with our unit circle. Periodic functions, which will have something we'll call a cycle and a period. And we will also be finding the exact value of trig expressions. So that's going to be a little bit of review as well. So let's go ahead and define first circular functions. Circular functions, we'll also sometimes see those as functions on a unit circle, which is maybe a little bit more descriptive. Basically, these are functions that are defined with the terminal side of some angle, again theta, and standard position intersecting the unit circle at some point P is our generic point with coordinates x and y. And we know because we're looking at the unit circle that x corresponds to the cosine of theta and y corresponds to the sine of theta. So symbolically we'll represent that, and this might be really the simplest way to add this to your notes. Circular functions are defined like this. All of our points P or whatever our names of the points are on our function, their xy coordinates are also the cosine of theta and the sine of theta when theta intersects the unit circle. So let's look at a quick example here. Our example starts with giving us the terminal side of some angle. It should say some angle theta in standard position intersects the unit circle at point P, where P is given by the coordinates square root of 7 over 4 and 3 over 4. We want to find the cosine of theta and the sine of theta. And this is relatively simple. We have a graph of that exact image here, or of that exact angle here. But remember that if this is a unit circle, then our x-coordinate is the cosine of our angle, and the y-coordinate is the sine of our angle. So I could say that the cosine of theta, therefore, is equal to the square root of 7 over 4, and the sine of theta is equal to 3 over 4. Not too bad. Let's maybe complicate things just a little bit. I'm going to look at another example. This time we're still given some angle in standard position. Let's see, I've got some messed up things here. Some angle theta in standard position intersecting the unit circle, this time at the square root of 15 over 4, comma, negative 1/4. We want to find the cosine, sine, and tangent of our angle. So I find it helpful to sort of sketch this angle out and maybe even end up drawing a reference triangle like we did when we were labeling the unit circle. So that means, let's see, what is the square root of 15 over 4? Well, the square root of 15, I know that the square root of 16 is like close, well, is 4. So the square root of 15 is close to 4. It's like a little bit less than 4. So maybe like 3.9 something, in fact. Now, negative 1/4, I can sort of estimate where that is. So I'm looking at basically 4-ish over 4, or 3.9 something over 4, comma, negative 1/4. Let's just estimate where that might go on my plot here. So let's see, I'm going to estimate that if this is 1, we'll label that 1, then my x-coordinate is somewhere down here. It's like really close to 1. It's a little bit less than 1. Now negative 1/4 though, if this is perhaps negative 1, then we could say negative 1/4 is about here. So I'm going to plot my terminal side of this angle right about there. Okay, so this represents in some way the angle theta. Now I want to find the cosine, sine, and tangent. I'm going to, like we did before, drop a vertical line to form my reference triangle. I'm forming my reference triangle. In fact, I might sketch this triangle just so that it's a little bit larger outside here. Let's say that this is just kind of a zoomed in version of that same triangle. So here's my 90-degree angle. Here's that point P. So I can label my three sides. I know that this point P is on the unit circle. So one aspect to remember about our unit circle, the name unit circle tells us that our radius and the hypotenuse of all of these triangles is 1 unit. Now the legs of this triangle are given by the coordinates of my point P. I went over horizontally square root of 15 over 4. So that is my x-coordinate. It's also my, my side length here, square root of 15 over 4. All right, similarly, my side length is the same thing as my y-coordinate, -1/4 here. And of course, our angle, here's our theta, always forms with the x-axis and our hypotenuse. Okay. So if we are finding cosine of theta, well, that stuff's easy. Cosine and sine, again, we can really just look back at our x and our y, because x is cosine of theta and y is sine of theta. So cosine of theta is just going to be that square root of 15 over 4. Sine of theta will be that -1/4. And that should make sense if we look back to our triangle. Remember, cosine is adjacent over hypotenuse. Our adjacent side is this square root of 15 over 4, and our hypotenuse is 1. So square root of 15 over 4 over 1 does indeed simplify to just square root of 15 over 4. All right, so now we just are left with the tangent of theta. And we can't necessarily read the tangent of theta from the coordinate point. There's only 2 values there, and those are already cosine and sine. So that's why having this triangle to look at is really helpful. Tangent, of course, from TOA of SOHCAHTOA is opposite over adjacent. Our opposite is the only side I didn't end up labeling over here. So that's going to look like then 1/4, I should say -1/4 over square root of 15 over 4. And that's definitely something I'm going to need to simplify. Remember, if I am dividing by a fraction, well, instead, I could just multiply by that reciprocal. So why don't we do that first? I'm going to show this work maybe in a different color. So I'm going to rewrite this as -1/4 times the reciprocal of square root of 15 over 4 is 4 over the square root of 15. So rather than dividing like we do when we have this complex fraction, we're now multiplying. And it so happens our 4's cancel out. They cross cancel. We also then see, well, we've still got some simplifying to do because we are currently breaking that syntax rule of math. We're not allowed to have the square root in the denominator here, so we have to rationalize. Here that just means multiplying both the top and the bottom by the square root of 15. What I end up getting is -1 times the square root of 15, or just -√15 over, well, this is going to be the square root of 15 squared. Remember, those are square root and squared. Those cancel out. So I'm left with 15. So the tangent of theta, therefore, is equal to the square root of 15 over 15. I forgot my negative. I'm sorry. Negative square root of 15 over 15. Okay. So that's how we would work with circular functions. Let's talk about periodic functions, which are very closely related, but maybe a little bit less specific. So periodic function is going to be any function that has a set of y values that repeat at a regular interval. One complete sort of pattern that ends up repeating would be called a cycle. And then the horizontal length of one cycle is going to be the period of that periodic function. So a good example is something like what's here, this kind of zigzag sort of graph. This would be called a periodic function. So what we are going to look for then is what exactly is the pattern, and if we're asked to determine the period, then how long does it take for that pattern to repeat? So that generally means picking a starting point. I like to pick right where x is 0, so I will pick in maybe a brighter color right here where my graph is crossing through -1, the y value of -1. So I'm going to look then, okay, so we go up, then we zig back down, and then we zag up and zig back down. Oh, we've already repeated the pattern. Notice here, I'm already back at my repeated y value, and then after that, the same pattern just keeps going. So my pattern is just that first, perhaps upside down V, just that first zig maybe of my zigzagging pattern. So I want to determine the period, which means what is the horizontal length. So I'm starting here at the x value of 0, and then it looks like, if I maybe erase this little dot, it looks like the pattern then hits the x value of pi. So it looks like we're actually working in radians here. This tells me then that the length of one cycle is pi. That is my period. I will end up writing that as p period equals pi. Okay. Oftentimes for periodic functions, we'll see the sort of units of our x-axis either in radians or degrees, but it doesn't always have to be so. Okay, let's look at one more example. Okay, here's a even kind of funkier one. I like this one because if we pick a starting point, then the question of when do we get back to that starting point isn't exactly what tells us our period. Notice that, okay, I kind of go up and then I go back down and then down. Okay, is that my period? Hopefully you're thinking no. That can't be my full cycle because I end up then going into sort of the negative y territory and then back up. The full cycle is actually this whole deal. That would be a full cycle. Notice that's actually what repeats. So I need to then determine what is the horizontal distance from my starting point, right at, again, x is equal to 0, until my cycle starts repeating, which looks like it's right at pi over 3. So based on that, we'll say that our period is equal to pi over 3. Okay, so you'll get some practice with that, identifying the period as well. And of course, we're just looking at the length of one cycle. Alrighty, now I do also want to talk about then another way that we will be working with exact values of expressions. We've done a little bit of this already, especially when we were using the unit circle, but there are other ways that we can find or work with the exact value of trig functions and make them more into expressions. So notice in my first example here, I'm not just asked for the exact value of cosine of negative 135 degrees, I'm asked for 2 times that. I first, though, want to figure out what is the cosine of negative 135 degrees. So I want to find this part first. That could mean sketching this angle, determining the reference angle, so on and so forth. Or if you've got a unit circle to refer to, then you could also locate this angle on the unit circle. So I might actually sketch it out just so that we get a little bit of practice with that. So I'm going to draw kind of a small set of axes. And let's see, if we're working with negative degrees, I know that my angle is going to go clockwise. It's going to end up going that direction. So let's see, negative 135, where exactly is that? If I can clean this up a little. Negative 135, well, that's going to be past negative 90, but not quite to negative 80. So I'm going to say that my terminal side of my angle will be right about there. And of course, here's our initial side. So there's my sketched angle. Now I need to determine what is my reference angle, which also includes like where exactly is that reference angle. So remember, our reference angle is always between the terminal side, this guy, and the x-axis, but it's always acute. So we're not looping back around. We're actually saying this angle here is my reference angle. So we're looking to determine what is the measure of that particular theta prime. Remember, that's what we usually call our reference angle. So the difference is, let's see, what is the difference between 180 and negative 135? Well, that's going to be 45 degrees. Okay. Now again, reference angles, they're always positive measures. So even though we started off with a negative degree measure, our reference angle is positive. We just have to remember exactly which quadrant we're in to then answer what is the cosine of this. Okay, so I'm going to sketch my little reference triangle and make that a little bigger so we can work with it. Here's my 45 degree reference angle. Here's my 90 degree angle. And I also know that if I've got one 45 degree angle in a right triangle, the other one is also 45. So here is our 45, 45, 90 special triangle. Okay, so I'm going to, like we said before, either artificially set that to 1 or just kind of assume that this angle is on the unit circle, which means our hypotenuse is going to be 1. And then because we're in the third quadrant, we're here in quadrant 3, both my, my x and my y, or my opposite and my adjacent sides, are going to be negative. So negative root 2 over 2, negative root 2 over 2. Okay, so that means the cosine of negative 135, that's also equal to the cosine of 45 degrees, specifically in the third quadrant, and that's equal to a negative root 2 over 2. Now I can't forget that the original expression here is actually 2 times that. So 2 times negative root 2 over 2, well, that could look like negative 2 root 2 over 2, or we can see that our 2's will cancel out. So we will be left with an answer of negative square root of 2. Okay, let's look at another example. We have now 3 times the sine of 150 minus 7 times the cosine of negative 45. So again, the task is really to find these guys first and then multiply them by 3 or by 7 and then find the difference. Okay, let's focus in on maybe the sine of 150 first. So again, I'm just going to draw a very rough sketch. 150 degrees, I know that's past 90, it's not quite 180. So I'll just sketch that my angle perhaps looks like that, which means my reference angle here is going to be the difference between 150 and 80. So that will be a 30-degree reference angle. Okay, that 30-degree reference angle means I'm working with a 30, 60, 90 right triangle. Let's see if I can draw that a little bit more nicely. So here's my 30-degree angle, right angle. Okay, we're in quadrant 2, so the x value is negative and the y value is positive. So I've got a positive 1/2 and a negative √3/2. Okay, therefore the sine of 150 is equal to a positive 1/2. Notice this is, of course, opposite that reference angle. And I'm just going to make sure that that hypotenuse is 1. Okay, so for now I'm going to leave that where it is. Let's look, though, at the cosine of negative 145. So here is my set of axes, negative 145. That's just like that. Now my reference angle, well, it's kind of the same angle, but we'll call it a positive measure. Remember, reference angles are always positive. So our triangle looks almost exactly like it did in the previous problem, but this time my reference angle, not doing great on the sketches here, let's see. Oh, there we go. My reference angle is up here, meaning this is my opposite, this is my adjacent, etc. And we are going to see the opposite is the only negative value. Our adjacent is positive in this particular quadrant. Okay, so our conclusion then is the cosine of negative 45 degrees. Well, that is equal to the adjacent over the hypotenuse, so √2, positive √2/2. Okay, so let's see what our expression then becomes. Now I'm multiplying the sine of 150 by 3, so 3 times 1/2, and I'm subtracting 7 times the cosine of negative 100 or negative 45, which is √2/2. Okay, let's see what we can do to simplify this, and I'm just going to sketch this up here. So 3 times 1/2, well, that's the same thing as 3/2. And let's see, I can also rewrite this as minus 7 √2/2. And because I've got a common denominator, I can go ahead and actually do this subtraction. I don't need to multiply either of these expressions by anything. They already have a common denominator. So we'll write our result is 3 minus 7 √2 all over 2. That would be our answer for that second example. Okay, so that's all we're covering for today. You'll see some practice with all 3 of those different concepts, and I hope you have fun. Thank you.